I will talk about some work we are doing on the concept of adaptive maps. And this concept heavily relies on this personalized route design problem. So I will focus first on this problem, and then I will move to the maps. Essentially, you know that a standard map provides a simplified representation of items in the real world, where these items are located according to their Euclidean distances in the real world. And as it is clear, such representation is not able to adapt to the needs of different users having different preferences. On the contrary, what we propose with these adaptive maps is that these adaptive maps are aimed at representing the world as seen through the eyes of the user, depicting, for example, the suitability or the difficulty of the path between points of interest according to the user preferences. So let me give you a couple of examples. You arrived, for example, to the city of Granada, and everything related with distance, the travel time, the concept of a pleasant walk, and so on depends on the eye of the beholder. So, for example, you can see here that to arrive to the main door of our cathedral, you can understand that this is a very easy path of 5 meters. If you are a tourist like this is okay. But if you are using a wheelchair, this represents a path of infinite length. Or moreover, you can say that there is no path here to go from this square to the main entrance. Something similar can be understood, for example, if you see this path in the mountain, which could be very hard for a family, but quite easy for an experimented trekking man, or this avenue looks very nice unless it is summer and the temperature is 46 degrees. Okay, so the question is if we can reflect this kind of information on a map. This work is being done in the context of this research project, where we focus on sustainable mobility, personalized routes, and adaptive maps. And the basic ideas are the following. We know that mobility is a key area for the development of sustainable cities, okay? And for example, we know that walking to work is significantly related to the environmental features. For example, the existence of accessible walking routes, such as sidewalks and paths. Also, we know that features like good environment or an appropriate route characteristics are significantly related to the decision of walking, for example, to work or just for leisure. And what it should be clear is that these concepts are user dependent and may vary according to his or her preferences. And essentially, we started to work in the problem of planning a journey, which is essentially or implies solving a routing problem that involves two kinds of aspects: quantitative aspects like the distance, the slope, or the route type, and qualitative aspects like the pleasant road or safe or whatever. And if you focus in routing problems between 2 points, between this point and this point, you can, for example, use any Google Maps application or something similar, and they will give you 2 or 3 routes depending on what you are trying to do. You can decide the transportation mode, but when having these results, you don't have any information regarding what you are going to find in the route. If you are going to find a path like this, or a path like this, or if you will have stairs, or if you are coming to Granada, you can find streets like this with almost no sidewalk. Okay, so instead of having one single map for everybody, we want to try the personalization of this map. So we started with the design of personalized routes, departing from a map and the preferences of the user. The underlying model is quite simple. We have a graph, okay? We have some set of points of interest, okay? And we have several features in every arc, okay? Like, for example, the slope, the distance, the type of the road, maybe some traffic information or whatever. So we have a directed multigraph, several features in every arc. We have the origin of the route, in this case, this point, the destination of the route, in this case, this point. And we also have constraints on certain features. For example, we can restrict to roads that have no vehicles. So we can eliminate some arcs, or we can put a constraint against the slope of every arc. And then we have a weights distribution that is used to reflect the user preferences. So initially, let me show you a very simple example. We have this simplified graph with 2 features per every arc. And we have this weight distribution. So what we are going to do is to combine the information in the arcs to obtain a single aggregated cost. And if you see now this plot, okay, right now the cost, the best path between 0 and 3 is not more the direct one. If we are going to work with constraints, well, we can put certain reference values, and then we can eliminate arcs that do not satisfy the constraint. We are working with real maps. So the underlying graphs we are using looks like this. Okay, this is the graph of Granada. We have thousands of nodes and streets, but more or less limit the number of points of interest. But we have here information at the street level, okay? Well, we started working with this problem. We had very nice results, and we realized that data is not perfect, okay? So in a second step, what we did in the past was to consider imprecision in the data. So we focused on the problem of design of personalized routes with flexible constraints. So instead of using things like, I don't want a slope greater than 1%, okay? This is the standard model. If we assume that imprecision is present in the measurements, the question is if we should discard a street with a 1.1% of slope. So instead of posing the constraints in this way, we will pose it in this way. The maximum slope I want is around 1%. Well, to deal with this kind of constraints, we use fuzzy constraints, which essentially allows for some violation of the restriction up to a certain point. And if we operate with this kind of things in a real map, we can define alpha as the degree of satisfaction of the constraint. And essentially what we get allowing this fuzzy constraint is to have more arcs in the map. And if we have more arcs, we have the chance to obtain better routes. So here is an example with different values of the satisfaction degree for the alpha constraint, where you can see the straight path is the this one is the one with the crisp constraint with a strict satisfaction degree. And if we allow for some relaxation, we obtain better solutions. Okay, here we have how if we use the standard constraint the distance is 4,600 meters. And if we relax the constraint, we can have shorter routes, okay? The same happens with the elevation profile of the routes. And what I want to highlight here is that we already have an adapted representation of the world using this very simple scheme. So the routes we obtain in this adapted graph, okay, reflects the preferences of the user, right? So when we solve problems on these adapted maps, the solutions are adapted to the user preferences. Now the question is if we can visualize this information in a nice way. And when you think on a map, we are used to think in maps where the objects are arranged according to their Euclidean distance in the real world. But other representations are possible. For example, here you have a map that shows the absolute increases in the number of residents who were born abroad during the first decade of the 21st century. The largest absolute increase is observed in Spain, okay? Followed by Italy and the United Kingdom and Germany, okay? So there are other ways to represent the map. And the general idea is as follows. We have the coordinates in the real world. This is the representation, the graphical representation, and we can move to the distance representation. In the situation where we are supposed to be given the matrix, then we need to detect where the points are. Okay, this is distance geometry. And the problem we have here is that the matrix we are given, okay, every single value in this matrix is calculated using the personalized route problem I showed you before. Okay, this matrix reflects the path suitability according to the user preferences for traveling from node A to node J. Okay, so now the question is, given this matrix, we want to find the new coordinates of the points. This is distance geometry, but here we have just a matrix of measurements. We don't have any metric space. In fact, none of the attributes represented in the arcs represent a metric space. So neither do their combination. So determining the potential embedding associated with this matrix is far from trivial, and as long as we know, it cannot be solved exactly. So as an initial approach, we applied multidimensional scaling. Although some conditions are violated, we want to see how the results looks like. So in order to proceed with the visualization, we first need to adapt the map. So if we have just one attribute in the arcs, then we calculate the best path between every pair of points of interest. If we have several attributes in every arc, then we combine the attributes, which implies a normalization and aggregation procedure. And then on this combined graph or adapted graph, we calculate the personalized route design problem for every point, for every pair of points of interest. Then we obtain the measurement matrix, we apply multidimensional scaling, and we will see how it looks like. Let's see some examples of what we can achieve. this is our simplified starting map. We have just 1, 2, 3, and 4 points of interest, the streets connecting them. We have 2 features per arc, and we construct our subjective matrix from individual measurements. So we have the best path between every point using just the first attribute, and the best path between every pair of points using the second attribute. If we calculate multidimensional scaling over this matrix and over this matrix, we have this representation. Okay, so in the map 1, which is associated with the first attribute, everything looks closer. For example, point 1 looks closer to point 2 than if we look at it using the map number 2, which is represented here in green. Okay, the same is happened between point 2 and point 3 according to the second feature, to the first feature, and this point 2 and 3 looks far apart if we consider the second feature. So this is the idea we are trying to capture. If we consider combination of the attributes, we obtain again different visualizations. So for example, we have here this matrix number 3 is constructed using this set of weights. Both attributes have the same level of importance or relevance. And in this one, most of the weight is assigned to the first attribute. So we have here a different visualization of the points. And what's the meaning of this kind of matrices? For example, we can have here this standard map, okay, where the points are located according to the Euclidean distance in the real map. And you have here, for example, the distribution of the same points according with the time needed to reach one point from another using a bicycle. So if you are moving on a bike, everything looks closer than, for example, if you consider the time by foot. Okay? Here is the distribution of the points using the distance matrix calculated on foot, and this is distance using a bicycle. And of course, one expects some correlation between these plots on distance and time, but this is not always true, because some points, for example, in the distance, you need to consider the direction of the streets, where this is not the case when you are walking. This visualization is, well, interesting in our opinion, but we want to go one step further, and we try to put these points on a real map to see how they look like. So essentially, we need to apply some techniques for computer graphics to use a sort of texture mapping approach, where the image is triangulated. Okay, we have here the points of interest, and we need to distort the image and map every triangle in the original map to a position in the new map. So this map here transformed to this. This is the original map, and we can see here how the map looks like when we constructed it according to the time, the distance by foot between every pair of points. Okay, so for example, the distance between this point and this point looks bigger in the real map than if you consider that you can reach the points walking. Here is the distance on bicycle map, okay? and the time on bicycle. And for example, you see here the distance between this point and these points looks shorter than this relation regarding time. And here is a problem that we think it has no solution, because we have here a slope. The point number 9 is the top of a hill where the Alhambra Palace is. Okay, so in order to go from here to here on bike, it takes you a long time, while the other points may look closer, like this one and this one, which looks closer here. If we construct the adaptive map using combinations of the attributes, we can visualize them. This is the original map, okay? And this is a visualization of an adaptive map considering upward, downward slope, and the distance. And under this scenario, point 3 and 4 looks closer than in the original map, because this area is almost flat, okay? And the path is not so long. If we look at this plot, okay, the preference are oriented towards avoiding areas with motor vehicles and minimizing the distances. So the distance between point 2 and 5 here looks closer than here, okay? And this is something that we all experience. When you have to walk in a pedestrian area, okay, everything looks closer. It seems that time goes fast, okay? It's a pure subjective feeling, but it is what we are trying to reflect. Well, this is nice, okay? This is a nice approach, but we were doing some tests with users, and the visualizations provided are quite challenging for the user, because they are not easy to understand. And this is especially true when several attributes are combined. So the problem is that when we are looking at a map, we associate the stuff with the Euclidean distance. Okay, there's some sort of automatic mapping in our brain. Although in this kind of things, it's easy to understand that everything looks closer if you move with a bike than if you move by foot. This is not so evident in a map like this. Okay, so the question now is the following. Is there something in the middle between this representation and this representation? And what we are exploring now is this kind of maps. I found these maps are called metro minuto, okay? Like meter and minutes. And it adds information, not just in the nodes, but also in the arcs. And the color in the arcs reflects some measure that can be different from the distance. So, and here is where I bring just a problem and not a solution. Maybe you can help me with this. What we are trying to do is the following. We have a set of points of interest, okay? This in the real map. We have the underlying graph. And initially, we don't want to compute the personalized route among every pair of points. So instead of this, we will consider just some pairs, okay, of points that are obtained after applying the Delaunay triangulation over the set of points, okay? Why? Because we need to display the map, and we cannot plot a complete graph here. So we need to define which arcs we want to plot. This is the first approach we are trying to test. We will plot just the arcs corresponding to those given by the Delaunay triangulation, okay? So we compute the distances between, not the distances, the best path between every pair of nodes, and we can obtain things like this. This is the original solution we obtained when we apply multidimensional scaling, but it appears rotated. You have here point 1, 2, and 3, and here we have 1, 2, and 3. So a realistic visualization would be like this. So the problem setting we are trying to solve now is the following. We have a set of points of interest, okay? This is the point of interest. But the main difference between the problems you are used to solve is that we know the original set of coordinates. We know the position of these points, okay? Now we can construct the subjectivity matrix, which will be a sparse matrix, because we will just compute some pairwise best path. We can define 3 points of reference, for example, this one, and this one. We think that we can use a sort of grid to map the points, and we want to pose constraints like this. So, for example, point number 7 is northeast from point 1. And point 7 is northwest from point 3. And point 7 is south from point 12. So the problem we are trying to solve now is to find a new set of coordinates as in distance geometry, okay? But also minimizing the difference between the new position of the points and the real position of the points. This is what we are doing right now, and here is where I want to ask you the following question. First one is if this kind of problems would be of interest for the distance geometry community. And the second one, if you know any available algorithm that we can apply. We have all the data, okay? Or maybe you can find, or you are aware of a similar problem. The previous speaker posed something not exactly the same, but in his slide number 25, he talked about the similarity matrices, okay? We are not sure how to proceed here. And what we also always have in mind that regarding these adaptive maps, all depends on the eye of the beholder. And if you think on a tourist, maybe we can think on maps where the distance between points is more important than the difficulty to reach them, or we can construct maps according with bike times, or maps oriented to a situation like this. For example, a tourist with the family is trying to go out, so he wants to see in a map just the points of interest that are reachable with a small slope in the path and just or at most 5 kilometers away from the hotel. It is clear that we have on one side optimization problems, okay? On the other side, we have visualization problems, and this is especially true in our case, that we should be very careful with the interpretation of results, because it is not so relevant for us to obtain the mathematical optimum of the problem, but a good solution that can be useful when visualizing, okay? Because we want to provide a proper visualization of the work. And that's it. I have here some references where you can check the details we have in these adaptive maps. And that's it. Thank you very much. If you have any question, any comment.
Thank you very much, David. So, any questions from the audience?
Yes. Is there any relation to your problems and the traveling salesman optimization problem?
No, it's not a TSP problem, because first, we don't have distances, okay? We have some sort of cost, and we don't need to visit the points. We just want to, we are not organizing the routes. We know the cost between 2 points. That's all the information we have. But we don't need to make a trip around the points.
The tourist has to make a trip.
But just between 2 points.
It's more a shortest distance problem.
Yeah, but we cannot talk about distances.
So is dynamic programming? It seems to be a dynamic programming problem.
No, but the problem is not for us to obtain the best path between 2 points. Okay, the problem is having the cost between every pair of points, how we can visualize them. Routing is not a problem for us. We know how to do it.
And David, I noticed that you have constraints sometimes.
Sorry?
You know, in one of the maps, adaptive maps that you showed just before the open problem, I remember you had the constraint a little before. Yeah, here, the next slide. Yeah, here you have you adaptive map 2. You're trying also to avoid the areas with motor vehicles. So this is a constraint that you add.
Yes, but it's a fuzzy. It's a fuzzy constraint, because if you just eliminate the arcs, maybe you cannot reach the points.
Okay,
so
I see.
Have infinite distance.
Okay, so it's like eliminating the arc. So it's a 0-1 information. It's not a penalty.
Well, essentially, you can consider it as 0-1. The arc is present or not, but we have some threshold over these values.
Okay, I see. Any other questions from the audience? Some ideas about questions that David asked. In fact, the last part is a quite interesting problem. Now, I have something in mind for the available algorithms, but let me think about this a little more instead before I say something that is forever recorded on YouTube and we cannot delete it.
Okay. Okay. Yeah, the idea is that we want to minimize the perturbation on the location of the original points in order to display the features needed by the user. Okay, but the spatial relation between the points should be kept.
Yeah, I see. And also here you have constraints. I see the 0.7 northeast with respect to P1, for example.
Yeah.
Yeah, this is from a mathematical point of view, how you can formalize this. I mean, it's an orientation. It's not a distance.
It's orientation, yeah, because we just want to conserve the spatial relation. We don't care too much about the distance.